So welcome back, everyone. So let me first by kind of just say a couple words about what we're going to do today, and then I want to have a discussion about the quiz, which is coming up. So next next Monday. So let's see. Let me get rid of that. Okay. So this is where we are in the schedule. We're in the middle of the linear algebra review, and so today we're going to finish talking about norms and then stuff about linear independence, and kind of we'll talk about what that means for rank, and we might get into some other stuff. If not, we'll cover that stuff on so next week Monday. So the grades for homework 1 have been posted. Those are posted just before class. So if you haven't seen those yet, they should be just posted. And so as I mentioned, so I think in the last lecture, I'd hope for the grades to be slightly higher. I think the homework 1 was maybe also a little bit harder than probably I should have calibrated for. Some things were trickier than they should have been. I think homework 2 will be more straightforward. After the lecture today, you should be able to do almost all of it, so you can get started. It's not due for a while still, until October 7th, but you might as well get started on it so you can do that. And then something we will do in class today, we'll go through how to do some of the linear algebra stuff inside Python. We're going to use this Collab file right here. So I think I turned sharing on for this, but you should be able to click on this, and it should be able to open up on a notebook that you can see and work through. If I don't have the sharing on that, please turn on properly. Please let me know. So then the first thing I want to discuss is going to be quiz number 2 and the relation to quiz number 1. So I had suggested posting of having as part of the quiz is 10 points out of the 100 points on the quiz, of you having a cheat sheet that you would make to help you study for the quiz, and then you would turn that in as part of the quiz. And I'm not specifying what has to be on it. Frankly, if you turn anything in that is at all relevant, it would count. So then I had asked for a discussion on this. It should be pretty simple to do if the file is going to be on your computer, but might be tricky if you just have it on a piece of paper. Then you have to take a phone, you have to load it on your computer, and then upload from your place where you're actually taking the quiz. The goal is not to put a burden on you, but I think this was something I instituted a couple of years ago in my other courses I taught. And on quizzes, people seem to do better on the quizzes. And so I thought of trying to put this back in some way, but I realized with the technology, it's not perfect. So there's been some discussion on Canvas about what to do with the quizzes. I think the first one was too hard and probably took too long, because just using the Canvas quiz made the questions a little harder in some ways. And they may have been a little harder than I had, probably should have had them. I think we've recalibrated this correctly for quiz number 2, but I'm open to ideas and suggestions on this. So I'll plan to have a proposal, which I'm going to try and get you all to vote on in some way. But I'd if there are any more points of discussion that have not been heard, now's the time to say raise your hand in the participants window, or to post something in the chat. can also continue discussion over Canvas as well. So, okay, so it seems like, you know, there were a bunch of good points in the discussion. I'm definitely open to trying new things, but I've thought some about these issues, and you know, I want to do what I think will have you best learn learn stuff for the course. I posted in the last discussion actually a number of questions in the book, which I think are, you know, at least somewhat representative of what will be on the quiz. There are different constraints when using a Canvas quiz. We're still trying to figure this out. So, okay, so I have two proposals with respect to the cheat sheet. Yeah, so let me do this here so I can actually write this down. And so the first proposal, which is going to be, so yes, so you have two buttons you'll be able to vote. So yes is that the cheat sheet is going to be worth 10 points. Okay, and so this is something that you would turn in, and everyone has to turn them in. And if you don't turn in, you lose 10 points, right? So it kind of forces you to do it. I've figured out one way, which is that we could implement this. That's not going to be too complicated or too strenuous, I think, to actually implement. Is that we can make the cheat sheet so it's optional. Okay, so the cheat sheet is optional to turn in. So, and you can get 5 points on top. I might have to make it worth 1 point. I haven't quite checked this yet, but it's you would get 5 points on top of your score, but the max score is still so 100. So okay, so it would give you 5 points in addition to whatever you do on the quiz, and think of this as a way to do partial credit. So if you miss something but you filled out a good cheat sheet, we'll give you 5 points on top of the score. So it'll be out of 100 points you can earn. You can earn 0 to 100, but then you would get 5 points on top of this. But we will, if you get above 100, we'll cap all the scores at 100. We'll have to go through manually and do that. So okay, so the second one is more of a soft option. You get rewarded for doing it, but if you feel this is not a good use of your time and you feel you know the material, then you can skip doing this also. Right? Okay, I think the easiest way to do this is to do kind of a yes/no vote in this. Okay, and I think you can either click in the participants menu, you can click on yes or you can click on no. So I just clicked on yes, I clicked on no, you can see this, and I think we'll get some votes. And I can see, it looks like you can see the tallies. Peter, can you see this also? Yeah. Okay, great. I'll try and leave this voting open. It is neck and neck. This is a close vote. Only about less than half of you have voted so far. What the first option, would the max score on the quiz be 90? The max score would be 100. Yeah, it would be out of 100, but there'd be one question worth 10 points for the yes option. There's a question on the quiz worth 10 points, which is upload a cheat sheet. That's what the first option is. So it's worth more of your grade with the first one, but it will. Okay, so this is.
Where is the voting happening?
What?
Where is the voting happening?
So you have to go to you have to click on participants in the Zoom one of the Zoom controls, which show up on the bottom usually. And there are 51 people who've logged in. And okay, there's some no in the chat. Yeah, but I'm gonna try and vote So I'll try and aggregate the votes, and then we'll see what we can implement. Right now, the no's are winning, but still, okay. So now most people have voted. I've gotten 40 votes out of 52 people here, and me and Peter haven't voted yet. So it looks like the no option is winning. There are 25 people who voted. That's over half. Yes. Okay. What if we get 100 points option 2 and turn the cheat sheet? Yeah. If that happens, if you end up getting 105 based on how we do the grading, we'll go back and manually round everything, cap everything down to 100. Right. So yeah. So I don't want to. Otherwise, I don't know. There's other weird things that can happen that way. But there's like a fudge thing in the bottom of the grading where I can add in 5 points at the bottom, I think. So okay, so it looks like this no option, this option here seems to be the winner. We've gotten, it was basically, it looks like I crossed it out, but this was, I see 27, and this one is 16. So we'll plan to go with the no option. I will make a Canvas announcement and update the quiz later tonight. Yeah, so we'll try and go with this. We'll see how it goes, and then if it's weird, we may try and reevaluate on the next quiz. But this seems like a reasonable option. Good. So it's kind of I'll encourage you all to make the cheat sheet, but it's not going to be kind of strictly required. But I think it's a good way to study. Also looking at the book. Also, hopefully, I've calibrated the quiz a bit better. Peter was not involved in the making of the quiz, and he finished, including reading and interpreting the questions, in I think just like 3 or 4 minutes. So hopefully, hopefully, I expect Peter to do, he's a smart guy. He's your TA. I expect him to do a bit faster than most of you, but hopefully it means the average time is 10 to 15 minutes, which is what I intend. So great, good. So any other questions about this stuff, or should we go on with the lecture? So good, great. Okay, so I'll explain it in detail again over Canvas just so everyone's clear. But hopefully you make the cheat sheet and turn that in, and hopefully it's a win-win for everyone. Great. So okay, got that thing on there again. Oh. How do I, okay, good. So we're talking about, kind of linear algebra review, and we finished, so the end of the lecture on Monday talking about norms, okay? And I started by talking about, vector norms, and let's say I've got a vector V, which is in RD. For instance, V is going to be equal to V1, V2, up to VD, okay? And so the norm is with respect to the vector. We should think about this as somehow measuring the length of the vector, okay? And so the first norm we talked about was written, this is the norm notation. You can just write that in text or in LaTeX. Even just writing that in text is fine, but in LaTeX you can do it. Actually the proper way is /v/. It looks a little bit better in LaTeX if you do it that way. So this first norm, is by default is the 2 norm, and that was just the sum over all the coordinates of VI squared, and then I took their square root. Okay, and then I mentioned that in general, we're going to have this VP norm, which is going to be, again, the sum over the coordinates of VI absolute value to the power P, and all this quantity to the root 1 over P. right? So in the case of the 2 norm, then the power 1 over p, right? This power becomes a square root. Okay, it's what you're typically doing, but you can raise something to a different fractional power. This is, you know, hopefully you've seen this before. Otherwise, it's like it's kind of weird, but it's something you can calculate, and it balances out the power to p, which is usually so. And so these are well defined. These are norms for these are good basically for p value from 1 up to infinity. Okay, and there are 2 common other norms which show up in this, I think probably in this course. So the 1 norm is going to be equal to this is, you can kind of write this down. It's just VI, the absolute value, right? It's the sum, and then this outside the 1 over p, the pth root is a 1th root, which doesn't do anything, right? So this is just adding up the coordinates. And then there's also a common definition called the infinity norm, which is basically the LP norm, what happens as p goes to infinity. Okay, and if I look at the expression for the LP norm, what's going to happen is I'm raising stuff to a really huge power. Think of raising it to a power, so to a power, say something like 100. And then I'm going to take a 1 over 100th root. Okay, but what's going to happen is the things that are slightly bigger, the coordinates which are slightly bigger, are going to be made huge, absolutely way bigger than everything else by taking to the 100th power. And then I take the 1 over 100th power and I bring it back down to what it was. And so the largest coordinate dominates everything. So this is defined specifically as just max of I in 1 to d of just the largest absolute value of a coordinate. Okay, so the L infinity norm is just the largest coordinate, the absolute value of the largest coordinate here. So, okay, so let's, so I'll go through a different example later, but let me just say that for this vector 1, minus 6, sure, we can use minus 6 and 3. Okay, then let's start with V1 norm. That's pretty easy. I'm just going to add these up. So that's absolute value of 1 plus absolute value of minus 6, which is 6, plus 3. And this is going to be equal to 10. The 2 norm is going to be 1 squared plus minus 6 squared. This minus, when I take a minus 6, I'm getting the absolute value for free because I'm squaring it. So that's going to be 36 plus 3 squared, which is 9. All of the square root of this, which is going to be 4 to the square root of 46. And so this is going to be approximately 6.8 something. Right, so slightly smaller than the L1 norm. Okay, if I did that slightly less than, that's my guess. Maybe someone could tell me the exact value. And then the infinity norm is just going to be the max absolute value, which in this case is 6. Okay, and then there's kind of a picture you can think of here, where if this is the origin. Okay, let me just draw this on a different page. Okay. Okay, so I can think of just in 2D, this is the x1 coordinate, the x2 coordinate. This is 0, 0, right? And I can think of a vector. This is my vector v. Okay, so the 1 norm is measuring this straight line the L2 norm, is measuring the straight line distance. The L1 norm is measuring the sum of, so this is the sum of these two lengths. And the L infinity norm, this is the max of these two lengths. So let's say the x coordinate is slightly bigger than the y coordinate. Let's say that this is equal to 4, 3. I may not have drawn quite that, but then this value would be equal to 4. This value would be equal to 7. And this value would be equal to 16 plus 9. That'd be equal to 5. Great. Okay. So there's another way of thinking about this, in that if I want to draw a circle where all these distances are, the space where all these distances are distance 1, then I get these different shapes. So if I draw a distance 1 here for the L2 ball, it looks like this. It's a circle. The things where things are distance 1 is exactly a circle. But with the things where distance 1 for the L1 ball is going to look like this. So the L1 ball is inside the L2 ball, and then the L infinity ball is like this, where any coordinate is a distance 1. Okay, so is the x or the y coordinate is the distance 1. Okay, and there are higher dimensional generalizations of these. We don't need to think too much about these now. When you deal with kind of types of regularization, you'll see in a machine learning or a data mining class, these become very important though. But I'll just kind of throw this picture out there for now, in case that helps you understand what's going on. So one reason these are important is that norms to distances. So I can say the distance between two vectors v and x. I can say that the dp distance is v minus x, this norm of this vector, right? So I can think of having kind of these two vectors. This is v is here, and maybe x is over here. It can be negative, and then I can look at, this guy is x, and then I can look at v minus x. This is v minus x. I think it's after it's been translated to start at x, but the same length. And so if I look at the distance between v and x, I can measure it in any of these norms, and it's a valid distance. Any of the p norms and the L infinity norm is what satisfies these metric properties of distances, which I'm not going to totally go into now, but they all satisfy this metric property. There's like a triangle inequality involved. They're symmetric. They're always greater than 0. These are all perfectly reasonable distances, and there's not one which is right and one which is wrong. You could use any of them. It's a modeling choice of which one is the right way to say which is the right distance. We spend, if you take the data mining class in the spring, they'll spend like three or so weeks on, what are these different distances? And you can look in chapter 4 in the book about this. Yeah, so v and x are both vectors. Yeah, so this is the case where v and x are both in RD. And in this example, they're both in R2. Yeah, so these are both vectors. I can say the difference between these vectors, or I can think of them as data points or a bunch of attributes I've read for one of my data elements. Yeah. So okay. There are norms for norms for matrices as well. Okay, so and it's often useful to think of a matrix norm, and this tells me something about the scale of the of the matrix. And they're you know, unlike vectors, there's a kind of a probably an even more complicated array of different norms for matrices. We're going to talk about two different norms in this for matrices in this class. Okay, so what's often called the spectral norm. So this is a matrix in Rn times D. The spectral norm is going to be a 2. This is often called the 2 norm of the matrix. Okay, this is going to be, so let's say this is going to be max of any vector in Rd where x is not equal to the all zero vector, ax, and this is implicitly the 2 norm, divided by the norm of x. So sometimes you enforce that the norm of x is equal to 1, and then you can not worry about this, the denominator. Okay, so, and it turns out this is equivalent to the max of y in Rn, y not equal to the all zero vector of y. Now it's a left multiply a to, okay, so what is this doing? This is kind of taking, now it's defined weird with respect to this max, but what it's doing is it's kind of taking the one direction or matrix, and because I've divided through, because I have this denominator here, I'm taking out, this takes out this, this takes out the scale of x or y, right? So I'm removing the scale effect from x or y here. So then it's just telling me what is the direction of x or y that can make the resulting norm of a as large as possible. What's happened is this vector inside of here, a times x, this is now a vector in Rn, and this one is a vector in Rd, right? So when I've done a matrix vector multiply, I'm actually, I'm turning it back into a vector, okay? And so I can turn it into a bunch of different vectors, and where I start with x, it turns it into, you know, the direction of x turns it into a different vector. And I want to find the vector where a can skew that vector as most as possible. Yeah, so this will be the maximum singular value. This is equivalent to the maximum singular value. We'll talk about that later in class. We'll have a lecture when we talk about dimensionality reduction. That's when we'll talk about singular values. Hopefully you've seen them before, but we'll kind of talk about them in the concept of data. Yeah, so it's equivalent to that. Yeah, so the different metric spaces. So a matrix is in an n times d dimensional space, right? So I'm looking at the space of matrices, and I'm trying to measure how big are these matrices. And basically one way to think about it is, and we'll talk about this in the context of singular values a bit more, is that, you know, if this is in a space Rd, a matrix is going to be a whole bunch of data points. Think of these as each of the rows. And then there's some sort of, you can kind of fit some sort of ellipse on these data points. And we'll see this, the singular value decomposition basically gives this for you. And this is basically the maximum, the maximum axis of this ellipse. That's kind of what it's describing. We'll think about this a bit more later in the semester. Is the equation of the max of y, is that y or g in the numerator? That is a y. Yeah. Everything that looks like a y or g, if I erase it, it's going to mess up the highlight, but everything that looks like a y, that looks like a g is actually a y. Yeah. What the norm of ax is. Okay, so ax Yeah, so great. So this AX here, right, and it's similar to this YA, right? If you remember, AX is going to be equal to A1 dot X, A2 dot X, AN dot X, right? This is a matrix vector multiplication, and it gives me a vector in Rn, right? So the result of A times X is a vector again, and then we know how to take vector norms, right? So this is allowing us to build on top of the vector norm stuff we already know to define a norm for matrices. Okay, so that's how to think about it. If we only knew how to do vector norms, how would we define a scale notion for matrices? And this is one way of doing it, right? So we're just taking the maximum of all these things. And it's a norm. It still works as the distance. It's kind of a strange distance, but I could do A minus B, right? And then that is still a matrix, and I can still take. It turns out that works as a metric still, but I wouldn't worry too much about that. We won't need to use that in the course. But so basically these green parts, what I've done is I've taken a matrix and I said, turn it into the longest vector possible without doing any weird scaling. I've taken the scale out of X by dividing through by it. And then I've figured out how to take the longest vector possible that results. And that's what this spectral norm is doing. The spectral refers to eigendecomposition, which is related to the singular decomposition. So we'll see that later in the semester. So, okay, so this is the spectral norm. There's kind of a simpler norm, which is maybe more natural, called the Frobenius norm. And so this is denoted with a subscript F. Okay, that's what's standard here. And this is probably more intuitive. Equals 1 to n, j equals 1 to d, a, I, j. Okay, so what have I done here? I've taken all of the elements of the matrix. I have to iterate over I and j, the rows and the columns. I've taken all those elements and I've squared them, and then I've taken the square root. Okay, so this is thinking of, I've got a square matrix and I've unrolled it into a vector. I've just taken all the rows and I've concatenated them all together to get one long vector here, and then I take the L2 norm. Okay, so this is probably easier to think about. It captures something more of a global scale of the matrix, but it doesn't say if it's long in any one direction, which is what the spectral norm does. Right, so this norm is, for me, it's probably a little bit easier to think about. It's more, at least computationally easier to think about. I can just add up all of the, so all of these, all these elements, and I've square them and then take the square root of all those, right? I need to take the square root because otherwise I'm dealing with some squared quantity instead of the same units I have going on there. Okay, so these are the two matrix norms that we'll typically use in class, and they kind of tell you in different ways how large this matrix is. So okay, so I want to say one more thing about vector norms. So before I forget, and then I'm going to jump over to the Collab and show a demo of this stuff, because the spectral norm, if I ask you to calculate how to calculate the spectral norm, the L1 or L2 norm of a vector, you can calculate that by hand, for instance, but the spectral norm is hard to calculate by hand. And so there's algorithms in Python that just do it for you. So we'll see how to do that. Well, later on in class, we will actually see how to one of the algorithms underlying how to get the spectral norm of a matrix, but we won't. But but we'll do that later on in the semester. Why is it useful to know a matrix norm? Yeah, so there are some quantities that kind of scale naturally with the size, the scale of the data, right? And you want to be able to kind of maybe factor those out, right? So that might be one reason. You know, in order to talk about, there'll be some algorithms that I don't know if we'll talk about them in this class or not. We might talk about this with respect to PCA or the dimensional reduction, but you might need to take one of the norms of the matrix. Definitely in, say, the machine learning or data mining class, you will you know, write down some algorithms, and they'll be approximation algorithms of some data represented as a matrix. And the right way to understand how accurate it is to factor out the scale of the matrix. And to do that, you need to take a norm. So that's one place where it will come up. You know, it's just one of these quantities that kind of, as you do more of this stuff, it seems more and more natural to do. But when you first see it, you're like, what's going on? But hopefully by the end of the semester, or if you take more classes, you'll see why this is just kind of a useful quantity to have. Yeah, so let's give an example here. Let me start with the Frobenius norm example. Let's say I have a matrix A equals 1, 2, 3, 4. All right, and then the Frobenius norm of A is going to be 1 squared plus 2 squared plus 3 squared plus 4 squared square root. And this is square root of 1 plus 4 plus 9 plus 16 equals square root of 29. Okay, I'll do another example in Collab soon. I want to talk about one other thing, a unit vector. Okay, this is something I should have mentioned with vector norms, but a unit vector is V in RD, so that the spectrum, the L2 norm of the vector is exactly 1. Is it 30? Thank you. Good. So the norm of the vector is exactly 1. So this would be kind of, sometimes I'll refer to a concept where I have the origin here, and I'll have a vector V, and I want to kind of take out the length component of the vector. I just want to measure what direction is it pointing. And so the typical thing to do is to say, here's a vector, and I want to take out the length component of it. So I will ensure that it's a unit vector. I'll say the length of it is 1. So it's not really capturing length, it's just pointing in some direction. And if the vector was not 1, I might say V is going to be equal to V divided by the L2 norm of V. And then that scales it down. So that could be that this would be V bar, and the original V might be this vector. And so it said maybe the length of that was 2. So I divide all coordinates. This is dividing all coordinates by that factor 2. And then it'll ensure afterwards that the length is going to be equal to 1. Okay, so this is a common thing to do to create unit vectors. And these will show up a lot. When you do a eigen decomposition or singular value decomposition, you're going to get some unit vectors representing directions. They'll be factored out from the scale component of it. Okay, so those are also important. So yes, okay. So let's see if I can jump over to Collab. And I'll just to remind you all, this should be, where is it? Right here. This lecture, if you click on this link, you should be able to get there. And so I'm going to stop this sharing and then do a different share here. Where is that? Where's the right screen I want? Ah, here. Okay. Okay, and I need to reconnect. Okay, great. So now I should be, your chat has, my chat's disappeared, but great. So here's this collab. Is everyone able to get to this if they click on the link? Give me like a thumbs up or something in the chart, right? And participants, you can give a thumbs up like that. If you can get access to that. So who is, okay, so I see at least, okay, great. 5 or 6 of you have gotten access to it. Okay, hopefully everyone can get access to it. This is good. You know, if you haven't done this before, this makes Python super easy. You know, this year a bunch of you came in with Python experience, but a few of you didn't. This means you don't have to install anything. You know, even if you want to use notebooks, installing like the Anaconda Jupyter Notebook Framework is like 1 gig of storage. I think I don't currently have it installed, even though it's super useful. But this, because you can do everything on Collab. So this just makes everything easier. Okay, so what you do, this is a window where I've pre-computed a bunch of examples, and we're going to use this this library called numpy, and you just import it like this, and this is a particular linear algebra subpackage that has some commands, and this gives you a shorthand. And so you need to first in here hold Shift and press Return while over this window. And this will take us, this will take a second because it's loading this library into the memory of whichever server of Google you're currently running on. Okay, and then and what I've done here, the first thing I've done is I've created an array V here. This is an array 1, 2, 3, 4, 5, and it prints it out. It will always print it out as a row vector. Okay. That's some kind of nuance of Python. So even if it's a column vector, it'll print it as a row vector. It's much more compact to read that way. I believe that is the rationale for doing that. Okay, and I can actually index into it. So this is indexing into index 2, and it prints out 7. So notice that means it starts counting at 0. So if I put in 0, I'm going to get out 1, right? Okay, so so that means you can, so keep in mind, if you're used to MATLAB starts counting at 1, NumPy in Python starts counting at 0. Okay. Okay, so let's see. The next thing to think about, you can create a matrix instead of an array. This is a 2x3 matrix. I think one we've used in our examples, perhaps. And it's, you know, it prints it out, and in this way here, it will distinguish rows from columns and how it's printed this out. And then, and you can index into it by the row and then the column. This is row 1, which is the second row, and then column 2, which is the third column, and that gives me 7. Or I can print out all of the rows with this colon, and then index into starting with the first row, which is with row 1, which is the second row, and going to the end, right? And that's where I'm going to get the translate down this part, right? So there are a variety of ways to index it. It's similar to MATLAB if you've seen that before. Okay. Here's the M. I don't know why I have this here, but okay. That's now a 3x2 matrix instead of a 2x3. And then, okay, so here's U, and then to add them together, you just add them, right? I don't need to write the code for adding them. You know, when I learned all this stuff, I was programming in C, and this was much more difficult. You had to write the code to do add. It's just a plus sign, and then you can print it out. And it's element-wise addition here, right? If I want to do element-wise multiplication, that's where I use the star symbol. right? This is not the dot product or outer product we talked about. This gives me an element-wise multiplication. This is not very common. It's not common that you would actually do this, but just to show you for what it's that it's not doing what was the dot product. The dot product, there's a number of ways of doing this. You can call the numPoint command dot, which takes in two things. This v is an object, so then you can call the built-in function dot of that object and apply it to another vector u, right? Or you can just do v at symbol u, right? This is actually the cleanest notation, and so I would recommend using this at symbol in most cases. It's much shorter than and less cumbersome than these other things. Okay, so then let's do another array B here. This is now a 3x2 matrix. And to do matrix multiplication, okay, so NumPy does not know if you put them next to each other, it means that they multiply. You have to somehow tell them to multiply, okay, as opposed close to the math notation. So again, we use basically this dot product symbol, or you can call this dot function. The matrix multiply is basically just a generalization of the dot product here, right? So so this is printing. See, these should this is B, and see, these are giving the same answer either way I did them. It's an example of matrix multiplication. Okay, to kind of see another example here, I can do matrix vector multiplication this way also. And you know, an array, a vector is a type of matrix. So I can just, you know, take the dot product. That makes sense. It would be the same operation. But that gives me for this. Now I have a B is a 3x2 matrix, and this is a two-dimensional vector. And so the output, when I multiply it, I'm going to get as the output a three-dimensional vector. Now, typically this would be a column vector. Okay, it would be the columns of B here, but I have, but it prints it as a row vector. Okay. Okay, good. So we're on to norms here. Yeah, so, you know, if I were to do something where I would do x dot b, right, what's going to happen? That's going to break because I can't do it on the left side. The sizes don't match, right? So okay, good. So let's fix that. Okay. Norms. Okay, so norms, I use this linear algebra package that I imported from inside of NumPy. It's a special kind of library within there, and you could call numpy.linearalgebra.something, or you can just import. I do this import trick, or from NumPy import linear algebra as LA. Then I can just refer to it as LA, and this is pretty. NumPy, you do this as NP, and linear algebra packages LA. This is pretty standard notation, ways people do it. And then I can do the norms here of the same vector V. Another example, if I instead did the v.2, right? The 2 norm, it's going to give me the same answer. So the default, without any parameter for which norm to use for a vector, is going to be 2, right? So that's why these are the same thing. The 1 norm here, let's print out V so you can see that. Yeah, so this is the vector 1, 2, 7, 5. So the 2 norm, it squared all these things, added them up, and took the square root, and I got something slightly less than 9. I wouldn't have wanted to have to do that by hand, right? So NumPy allows you to do that. The 1 norm is here, the one norm of the vector is giving me a v is giving me 15. Oh yeah, 15 because I've added all these up, right? So that's 1 plus 2 plus 7 plus 5 is 15. And then the Frobenius norm is going to give me 7, right? Because it's just the maximum value here, which is just 7. Okay. And then I also have these matrix norms, right? Remember my matrix A, 3, 4, 3, 1, 6, 7. Why isn't the inf norm of 7? Yeah, so the inf norm, you call NP inf here, so is actually 7. I did 2 versions of the 2 norm here, right? So if I do it again, I can add in some piece of code, but just so it's clear which is which. Print gives me 7. Yeah, good. So the one norm is 15 because I've added everything up. And notice that the one norm is always bigger than the 2 norm, which is always bigger than the inf norm. Yeah, great. Okay, so now let's look at the matrix here, matrix A. Remember 3, 4, 3, 1, 6, 7. The Frobenius norm of this is just squaring each of these, adding them up, and then taking the square root. That'd be kind of annoying to do, but gives me 10.95. Okay, and then the 2 norm of a matrix, I just put the 2 there, and it does this max operation for me. And it'll probably it's using some structure like the SVD, which it might do by, say, the power method, which we will see later on in class. But it does that automatically for you, built on kind of these classic linear algebra packages. And that's slightly less than the infinity norm. So it turns out that the infinity norm and the 2 norm are not too different in this case, but the Frobenius norm and the 2 norm are not too different. The Frobenius norm is always going to be the larger one here. Okay, it's got extra terms going on. Okay, okay. So the transpose. So if I print out a transpose of the matrix, yeah, it's transposed, and I can see that it's now a 3 by 2 instead of 2 by 3. It's changed the role of the rows and the columns. But if I do this with the vector x, when I print it does not show me anything different here. So this is kind of potentially super confusing, but ends up being quite convenient because if you're printing like a 10-dimensional vector, that's kind of long to print it the column-wise, but row-wise, it's easy to fit. And it's worth, let's say, 30 dimensions. It's easier to see what's going on with the row here. Okay, so that's okay. And so something we'll cover later on in this lecture is the matrix rank. We can get the rank of the matrix is going to be 2. There's a command. Basically, anything you think of, there's some built-in command. My examples in the book show you some of the ones that I think everything that really comes up in class, but pretty much anything you can think of has been built into this library, right? So you don't have to actually do a lot yourself. Something we'll talk about, I'll just quickly go through things we'll talk about next lecture. Yeah, so this is the inverse. Is also something you don't want to implement by yourself. A matrix inverse. This needs a square matrix. And so this takes this matrix C and it inverts it. You can see what the answer is here. And this should give you the identity matrix afterwards, which is 1, 0, 0, and 1. So it's only 1s on the diagonal, 0 elsewhere. And it doesn't quite do that. If I multiply a matrix C by its inverse, I should get back the identity. There's a little bit of rounding error, and it's decided it wanted to show me that rounding error. But it's to the, something in like roughly the 16th digit. So, okay, that's basically the identity matrix. Okay, great. So these are, we're going to, in this class, aside from when we talk about the power method, we're going to kind of pretend that these techniques are kind of exact. But the point to realize here is that they're kind of, they're often these numerical things under the hood where we're not going to actually get the exact answer. We're going to kind of converge to it. And at some point, we'll stop when we think we're close enough. And that's what happened here. So, okay, so we'll talk more about these iterative methods later in the semester if you haven't seen or been exposed to them before. So great. So any questions on the Python? Okay, so I'd like to encourage you to do this. I'm wondering, like, how many of you have actually were kind of doing this and playing with it as we were going? Can you maybe show me like a thumbs up again? 4 of you, including Peter, still have your thumbs up. Okay, that's a thumbs down. So someone decided not to do it. Was it a, you know, if there's a technical problem, kind of let me know, or if it's just you'd rather just watch me do it than go play on your own. But if you haven't used this before, I was surprised how simple and easy this is to use. You can use this on your homework. I think we made the questions, the numbers simple enough that you don't need to use it, but I recommend you kind of try doing this on the linear algebra stuff in your homework just to get used to it. You'll do a little bit more complicated stuff later in the semester, and this is kind of like your practice using numpy. So when we're doing other things, it's less new. Perhaps you've seen numpy before. There's a data wrangling class, which is a 2000 level class for creating that sits before this class, and that will probably go through a bunch of this, but most of you probably haven't taken that class yet. Yeah. So is there a function you can run on a vector to tell behind the scenes if it's being treated as a column or row vector? Yeah, let's see if we can do this. Not great at remembering these offhand, but I think size, let's see if size will tell me this. Yeah, that didn't help.
Maybe shape.
Yeah, let's try shape. Okay, I think shape is different. Let's try. It's kind of. Yeah, I'm not sure about that. Maybe with these things, the Google works pretty well to look things up. So yeah, but maybe Peter can look that up and post it in the chat. But Stack Overflow is great on this stuff. Most questions you would want to ask have been asked on Stack Overflow and been answered before. And the NumPy documentation is pretty good. So this stuff really is pretty easy to use. I definitely recommend you guys, trying to use this for your stuff. Okay, so let's go back to the rest of the material we want to cover for the lecture. Okay. And where is... Okay. Great. Okay. Yeah. So, okay, great. So, close my chat. Okay. So that was NumPy. It's super easy to use. Let's talk about the next important concept. This is a pretty important thing that we will definitely build on a lot through the rest of the semester. So linear independence. Okay, so this is a really important concept, one of the most important concepts in linear algebra, and how to think about these vector spaces. So we're going to consider now a set. Consider a set of k vectors. x1, x2, up to xk, and these are going to be vectors in Rd. And we're going to also have k scalars, alpha 1, alpha 2, up to alpha k. Oh, I used alpha and x look a little similar. I'll try and make sure these are I pick up my pen on those x's. Okay. Okay. And so this the really important thing with this, between these scalars and these vectors, is that I'm able to write another vector as the sum, as basically this weighted sum. And this vector will still be in Rd. Okay, so all I've done is I've scaled them all. That means the scaling means I scale every coordinates by alpha, and then I add them together. It's coordinate-wise addition. Okay, but this idea of doing this is kind of so going to be very powerful. Okay, so if I have, we're going to call this set, we'll call this set X. This is an uppercase X, right? Okay, so we're going to say that any vector z in Rd that can be written so like this, right? So as this sum of these scaled versions of a set of these vectors is going to be linearly dependent on this set X. Okay, so it means I can write it as a function of these other vectors. It means it's kind of not telling me something new. So the kind of the contrapositive whatever to this is that so any vector z in Rd that so cannot be kind of written kind of z equals alpha I xi is linearly so independent. Okay. Okay, so the ones which cannot be written, these are called linearly independent. Okay, and that means that they're kind of, if I can express more by including this vector z, that's kind of telling me something more than I have this vector x. So I couldn't write it before, but now I clearly could write it if I added that into the set x. If I added z into the set x, now I can at least write the vector z by just having a coefficient of 1 on z and 0 on everything else. So that allows me to express more. So that means it's linearly independent of these things. Okay, I'll do some examples and show some pictures that help a little bit. But let me say a little bit more notation about this first. So the span of the set X is going to be the set of these vectors Z, such that when I write this big vertical line, it means such that. So vector Z in Rd, that's, usually you do this vector Z in Rd such that Z equals 1 up to k alpha I xi, such that each of the alpha I is going to be in R. Right, so this span is the set of all vectors I can write with the set X. Okay, so is this just saying a scalar multiple of the vector X is linearly dependent? Right. Yeah, so if the set X is just a single vector, then it's just all scalar multiples of that vector, right? So if I just have, this is my basis, I've got a single vector, let's call this x1, then the span of x1, and the things linearly dependent on x1 are going to be all vectors along this line. They can be negative as well. I can multiply by a negative number, and that's how I get below the axis down here. Okay, but this blue line tells me the span of just this one vector x. And if I have multiple vectors, right, if I also have x2 over here, then what happens is the span ends up being this whole space here. It's all of the space R2. This is the span of x1, x2. It's the whole space here, because if I have a vector, say if I have a vector z here, well, I can write this by basically adding a negative amount. Let me draw that in pink. So a negative, this is like alpha 2 equals, say, minus, move this down, alpha 2 equals, say, minus 1.5. So I go down here, and then I do some up along the direction, if I did this right, let's say of, maybe it's minus 1. So alpha 2 is minus 1, and alpha 1 is equal to 0.5, right? So I'm able to get to z. Even though these are not kind of, they don't need to be kind of perfectly right angles to each other. As long as I do this, I can get to any other vector in this green space here. Yeah. Okay, good. Okay, so what this is describing is the so if the span of x is equal to RD, and x is a subset of RD, then we say that x is a basis of RD. Because, and what the basis means that I can represent any vector in the space of RD as some linear combination of these vectors. Okay, so this is important. That means I can get anywhere. It's like in this 2D example inside of R2 here, I can get to any spot by just these two vectors x1 and x2. Okay, and if you have d linearly independent vectors in a d-dimensional space, then those always form a basis. I can get anywhere with those. Okay, so let's see a little bit more about, yeah, let's go through an example, a hard example now. So let's say that x is the set of x1, x2. X1 is going to be the vector 1, 3, 4. X2 is the vector 2, 4, 1. Okay, so these are, unlike the picture I drew on the previous page, where in 1 or 2 dimensions you can draw pictures. We've gotten to 3 dimensions. We can't easily draw a picture anymore, but we can do this with linear algebra to kind of visualize what's going on in now this higher dimensional space, right? We're now in R3. Pictures become difficult, but we can think through this example. And then let's consider 2 more vectors, z1 minus 3, minus 5, and 2, and z2 equals 3, 7, and 1. Okay. Oh, take a look at the last slide quickly. Yeah, here's the last slide. I will, and again, I post these on the website as soon as I can after class as well. So you will get a chance to get back there. So, okay, so we have this example here. So now the question is Z1 linearly independent of X? Okay, so feel free to answer in the chat. If you think it's independent, say independent. If you think it's linearly dependent, then how would I write this? can I come up with some way to write this using x1 and x2? It is not independent is the first one. Okay. Oh, so it is not linearly independent. Yeah, good. So in fact, I can do this with coefficients 1 and -2. Right. So these are alpha 1 and alpha 2. Let's write this out. This is going to be 1, 3, 4 minus 2 times 2, 4, 1. And we're going to get -3. 3 minus 8 is going to be -5. 4 minus 1 is going to be 3. Ah, so maybe I made a. Oh, it's not. Oh, okay. I thought I tricked myself here. So let's see. I thought this was going to work, but I guess. Oh, yeah. So this should good. So this, yeah, good. So this one should be 2 because I do 2 times 1. Yeah, great. Yeah. So I've recovered this vector, and this is equal to z1. Okay, great. So let's do the same thing with z2. So am I able to come up with a linear combination of x1, x2 to get to z2? So no, I can't. Great. So why can't I? That's maybe harder to explain in the chat. But let's see. Let's kind of work through this. Okay, so it looks like I want to get z2. I want to get the first column to be 3, and the first element to be 3, the second one to be 4. If I did that, I pretty much have to have the first. I have to add 1. If I just add x1, x2 together, looks like I can do 1 here. Okay, so I do 1, 3, 4 plus 2, 4, 1. This looks like it's going pretty good. I'm going to get 3, 7, and then 5. But oh no, answer 5 is incorrect. That was supposed to be 1. Okay, and so if I have 2 coordinates, it allows me, if I have 2 coefficients, I can basically show I can always get any 2 coordinates to match. But that third one, it has to match at the same time. And if I get 2 to match, but the third one does not match, then it's going to mean that they can't be then they cannot be linearly independent. So okay, so yeah, so at this point in a linear algebra class, you probably spend a lot of time looking at how to compute these things, maybe with some tricks for evaluating this and Gaussian elimination. We aren't going to use those things in this class so much, so I'm not going to go over them. Okay, so just like there's a bunch of probability and statistics I skipped over, we're going to skip over how to do this in this part because it turns out this doesn't come up so much, and probably because if you have noise in the data, you often don't get these things exactly anyways. Yeah, there's some discussion on the chat about how you can do this, but we're just not going to go over that in the class. So okay, good. So here's kind of an example of how to think about it. Yeah. So okay, so then another just notation. We're going to say a set of vectors x, right? X1 up to xd is xn is linearly independent. Okay, so just like independence and probability, you could define it for events or you can define it for random variables that are slightly different. This means that I can, they're linearly independent if I can't represent any of the vectors by the other elements of the set. It means that if for all kind of xi in the set X, I can't, there is no alpha 1 up to alpha I minus 1, alpha I plus 1 up to alpha n, so that xi is equal to, for let's say j, for I not equal to j, where this is alpha j xj, right? So that there's no way to represent it using the other elements of the set. That means that each one of these vectors is needed. If I remove any of them, I've lost some information of what I can represent. So that means a set is linearly independent. Okay, and so if I have a linear independent set of n things, it means it's giving me a basis of n things. I'm not wasting kind of any information with the ones I've kept around. Okay. Yeah, so I want to quickly show, so I've got a couple minutes left. Quickly show another example here. Let's think of the geometry of this. So think I've got a matrix, A1, A2, and A3. And these are two-dimensional points, 0, 1.5 and 0, 2, and 0.5, and 1, 1. All right, so I can think of these as 3 points now, and that's going to mean I can actually draw, and they're in I can think of these as 3 points in R2, and I can actually draw a picture. And to think about this a little bit, and so we're going to have so that let's see, so A1 is going to be, this is going to be A1, this 1.50. Okay. A2 is going to be like 0.5. So this would be A2, 0, 2, 0.5. Think this as a vector here. And then A3 is going to be 1, 1. So it's going to be somewhere right around here if I did this correctly. Okay, think of this as a vector. Okay, it turns out these are not linearly independent because in fact I can draw a line that goes through them. Right, I can represent them as each other. Now, okay, so what's actually going on here is I'm always allowed to use the origin. I can always use the 0 point to represent other things. And the same, because I can, remember, I can scale along any of the vectors. So, but this would be true even if I added like the x coordinate was 0, right? Or the z coordinate was 0. So let's say instead I pretended that these were 3-dimensional, and then there was a z coordinate here that was 0 for all of them. Then this would be what would happen. But this is kind of a nice illustration that it's not just scale multiples, but these three are not linearly independent. So not linearly independent because there's this lower dimensional subspace, this light blue line, which is capturing all the information. So I could represent one as kind of the average, or not quite average, but a weighted average of the other two. Okay. Okay, great. And then, yeah, so I've one last thing. I'll just say this really quickly, and then we can repeat it next Monday. But the rank of a matrix is rank of a matrix, say A in n times D, is the maximum number of linearly independent rows or so columns. Okay, so turns out it's going to be the same number. If I have a matrix and I look how many rows can I pick out that are linearly independent, you know, the maximum I can do that with, that's going to be the rank. Okay, so that's what the rank is saying. In this case, the rank of these vectors is going to be 2 because I have the origin plus any 2. I can always get the third one. So one thing this means is that the rank of A is always less than or equal to the min of the number of rows and the number of columns. I cannot be more than n or d, and if the rank of A equals the min of n and d, then I say that this is going to be full rank. That means that it can represent anything in whatever the smaller of those 2 coordinates is going to be. Okay. So great. I'll probably repeat the stuff on rank and go through an example in the lecture on Monday, but this is how much I want to cover. So great. We'll continue with this stuff, talking about square matrices and inverses and stuff on the lecture on next week Monday. But this will be the end of the material that I could potentially ask about you on the quiz, and I will post some more details about the second option, how we'll modify how we do the cheat sheet stuff on the quiz. I still recommend you do it and look in the discussion for a bunch of practice questions in the book, which are going to be kind of the sort of topics that you could see on the quiz, but they'll be simpler than that. So great. I'll be around for office hours for a bit for any questions you have.